So the first thing that I'm noticing here is that we have this trig function being squared. So that tells me I need to do some kind of quadratic something. Whether that be factoring, I probably won't need to factor because it's just sine squared. But I'm thinking I'm going to have to do something quadratic related because of that squared term. So since we just have the sine squared and no other trig functions, I'm going to first work to isolate that sine squared. So I'm going to add 1 to both sides, making it 4 sine squared of x equals 1. And then I'm going to divide both sides by 4, making it sine squared of x equals 1/4. And so now to get it into a form of what we're more familiar with, we need to square root both sides. So square rooting, the left side gets rid of the sine squared, and so we just have sine of x. And then square root of 1/4, that needs to get simplified. So quick reminder of when we're square rooting a fraction, it's the same thing as square rooting the numerator divided by the square root of the denominator, where the square root of 1 is 1 and the square root of 4 is 2. But remember that when we square root, it's plus or minus, because positive 1/2 squared is 1/4 and negative 1/2 squared is 1/4. So sine of x needs to equal plus or minus 1/2. Basically telling us that we are describing the angles where sine of x equals 1/2 and then sine of x equals negative 1/2. Now for this problem, we are describing the angles between 0 and 2 pi, and since it's just sine of x and we don't have like any number in that we're taking sine of, the period for both of these is 2 pi. And so we don't need to do that end step for this particular problem. Okay, we're basically just plugging in n equals 0. So at this point, all I'm going to do is look at my unit circle and figure out at which angles do I see that sine equals 1/2 and negative 1/2, or where's the y coordinate, positive 1/2 and negative 1/2. So let's see, we're going to see positive 1/2 at pi over 6. And then in quadrant 2, that would be 5 pi over 6. And then we're going to see it at negative 1/2 at the same denominator of the 6, so that'd be 7 pi over 6. And then 11 pi over 6. Okay, so 4 angles within 0 to 2 pi that make this true. We don't need to. Because we're describing the solutions between 0 and 2 pi. So if this was like sine of 2x or sine of x divided by 2, then yes, that end step is what I'm calling it would be necessary. Okay, but not here. Okay, so not too bad. I think kind of an extension for what we did yesterday. The next few we're going to do are a little bit more complicated. And so at a quick glance, when I look at example 6 here, I'm noticing that there's a lot of trig terms in this equation. There's tangent of x, but that tangent of x is being multiplied to sine squared of x, and then it's equal to 3 tangent of x. Now, this is a term on its own, the tangent of x times sine squared of x. So a good place to start, and we kind of talked about this yesterday, is get all the trig functions to one side, essentially isolating those trig terms. So I'm going to subtract this 3 tangent of x to the other side, but know that it does not subtract away from this tangent of x because that tangent of x is being multiplied to that sine squared. So I'm just simply going to subtract it to the other side, and it just makes it a whole new term on its own. So tangent of x times sine squared of x minus 3 tangent of x equals 0. So even right now, there's nothing to me that's like super obvious. The only thing that I'm noticing is that both of these terms on the left-hand side have a tangent of x, and thus I can take out a common factor of tangent of x. So I get tangent of x times sine squared of x, and then minus 3. And again, we're seeing where that equals 0. So after taking out that common factor of tangent, one thing that I've suggested to us all year, that anytime we factor, do a quick check. If you were to distribute tangent of x back into this parentheses, do you get the equation that we had previously? And we definitely do, right? Tangent times sine squared is tangent sine squared. Tangent of x times -3 is -3 tangent of x. So I like that factor. The next thing I'm like, well, if I just factored, when we solve by factoring, we take each factor term and set it equal to 0. And it needs to be equal to 0 for this to work. So now, since this is factored, I can just let tangent of x equal 0 and sine squared of x minus 3 equals 0. And we're going to be able to get our angles from this right off the bat. So for tangent of x equals 0, remember we are describing the angles between 0 and 2 pi. So yes, the period here is pi. So I guess technically we are, let's do that like end step for this. So where do we see tangent of x equals 0? Where's y divided by x going to be equal to 0? At pi, because y there is 0 and x is 1. So x equals pi. It also happens at x equals 0. And you know what? That's it. Because the next value would be at 2 pi. And 2 pi, we're not including that angle. Okay? Because it's saying we're describing the angles that are less than 2 pi but not equal to 2 pi. So it's just simply pi and just simply 0. We actually don't need to add any values of n. All right, then for the sine squared of x minus 3, kind of like when we saw the sine squared before, I'm going to add 3. So sine squared of x equals 3. And then square root. And I get sine of x equals root 3. And so when looking at this, remember that we're describing an angle where we get sine to be root 3. Well, on the unit circle, what is the largest value that we can get for sine? The largest y value? 1. Root 3, I'm sorry, I had a note about this. So when we get here, we're figuring out at what angle does sine equal root 3, which is approximately 1.73. Well, the largest y value that we can get is positive 1. Okay, there's no angle that we can take the sine of that's going to give us a value greater than 1. And so because of that, we do not get any solutions from this part of the equation. Okay, so let's also just make a reminder that the range of sine of x is -1 to 1, meaning any angle that we plug into sine of x is going to get us some value in between -1 and positive 1. And with this y value being outside of that range, that's why we don't get any solutions from this part. So no solutions from this part. So the only two angles here are 0 and pi. Those angles still do work. And you can check that. If you plug them in, you should find that you get both sides to be equal. Okay. Let's take our 5-minute break now. Even though it feels like we just got started. I'm going to set my timer for 5 minutes. These take recognition. There's not going to be like an obvious thing that when you see this problem, you're like, oh yeah, this is exactly how I get started. You have to be willing to try something, see if that's getting you somewhere that does look familiar, and if it's not getting you anywhere, be willing to restart. And so the reason I bring this up is when I look at this equation here, I have a cosine squared, and we've done problems with sine squared and cosine squared, but then the second term is a sine. So at first glance, I'm like, I can't really factor this. Okay, I could only factor it if they were both the exact same function, or the exact same term, meaning both cosines or both sines, and we don't have that yet. So I'm thinking, might there be a way that I can replace either cosine squared or sine with the other function to then try to get this in a quadratic form that I can maybe factor? Well, we know that there's a Pythagorean identity. So Pythagorean identity. That says sine squared of x plus cosine squared of x equals 1. And with those identities, they can all be manipulated, meaning I can solve this equation for cosine squared. And when I do that, I have to subtract sine squared of x. And so that's how I'm going to be able to replace cosine squared in the equation with a sine squared, and then hopefully be able to factor it from there. So I'm going to subtract sine squared, so that makes this 1 minus sine squared of x. And so now that we know what cosine squared is equal to, I don't know what's up with the camera today. It doesn't want to focus. I'm going to replace that cosine squared with 1 minus sine squared. So this is 2 times 1 minus sine squared of x plus 3 sine of x equals 0. So this is starting to look a little bit more familiar since I have a sine squared and a sine, but the parentheses are kind of throwing me off, so let's distribute the 2. So 2 minus 2 sine squared of x plus 3 sine of x equals 0. And then I'm just going to rearrange these. So it goes negative 2 sine squared of x plus 3 sine of x, and then plus 2, just so that it's in that quadratic form. And then one thing that we did yesterday, and this is more just to kind of see how the u substitution to be able to factor this is going to work out, is I rewrote the sine squared of x as sine of x squared and then plus 3 sine of x. And it's not that you need to actually write this out. I just think it's going to make it more clear as to how we are going to sub in sine of x equaling u. And that's what I want you all to work through right now. So based on what we did yesterday, see if you can't take it from here. Substitute u in for sine of x, work to factor it, and then come up with our solutions from there. Give it a few minutes to work through that. Bottom left is all the factoring work. Your factors. So one thing that I maybe would have done as well is once I get here, I might have divided everything by -1. For the main reason of getting that a value to be positive. It's still factorable with it being negative. It's just one more thing we have to kind of keep track to get the same values. When I leave that as negative 2u squared and I get my 4 terms here, in the first grouping, you can take out positive 2u or negative 2u. It does not matter. I took out positive 2u. Outside the parentheses, so negative u plus 2, which matches that second grouping already. So for the second grouping, I'm still taking out a common factor, but that common factor is just a positive 1. Okay, and that positive 1 is what helps me when I actually go, Franco, no? When I take out the negative u plus 2, that second factor is 2u plus 1, not just 2u. Okay, that 2u plus 1. So then getting u by itself, you get u to be u is, which is sine of x. And so we're trying to find the angles where sine of x equals -1/2, which is that 7 pi over 6 and 11 pi over 6. And it equals 2. Nowhere. Problem. And we're all done for today. So this is another problem where when I first look at this, there's nothing obvious as to how do I get started. Okay, again, the one thing that really kind of throws all of these off is that we have a sine of x and a cosine of x. Now, if this was equal to 0, that'd be okay. If maybe there's an identity that I can use here to try to rewrite sine of x and cosine of x. So I'm going to go ahead and grab that identity sheet that I gave to you all. And I'm looking for something that might have sine and cosine. And I'm seeing sine and cosine down here in the double angle formulas. Now, we didn't do anything with double angle formulas. We skipped those sections, mostly so that we can get through some of the more important stuff. It's really just plugging things in, and it's not a hard thing. So some of the things we're working on today, and then also with some of the identity work you'll do on the review. The other ones that we might end up using are these power reducing formulas. I think either of those could show up with some of our solving and verifying identities. The half angle formulas, maybe those might show up, but probably not. Okay, so know that there are some extra identities on here that we haven't actually covered or worked with yet. Basically what we're using this for is, can we replace is I see that sine of theta and times cosine of theta, which is really close to what the left side of this equation looks like. The problem is, in order for us to use this identity, we need 2 times sine times cosine. And so what we can do to make that happen is we can multiply both sides by 2. Let's do both sides by 2. 1/2 times 2 is 1. And now we have 2 sine of x times cosine of x, which according to the double angle formula side becomes sine of 2 theta, and it equals 1. Or sine of, let's use x. We've been using x. Not that it really matters. We'll just keep it consistent. Sine of 2x equals 1. Right, and now this is a problem like just what we did yesterday. So remember, because these are the ones that tend to throw us off, when it's sine of all this as part of this. And so where do we get sine of x to equal 1? The y coordinate is 1, only at one place, right? At pi over 2. And then if we include the period of 2 pi n, we'll get back to that same y value of 1. So remember that this represents all solutions to sine of x equal to 1. But we want to is equal to 1. So we're going to let this 2x replace that x in that equation. So we have 2x equals pi over 2 plus 2 pi n, and then everything's going to get divided by 2. All solutions to sine of x, or sine of 2x, equal to 1. The 1 is what we're trying to figure out at what angles does sine equal 1. So it's not that it went anywhere. It's just that we know that we're going to get 1 when we take sine of pi over 2. Sine of pi over 2 is 1.
About the 1/2.
I multiply both sides by 2, so 1/2 times 2 makes that 1. All right, now we have this formula or this equation that describes all the solutions, but once again, we're describing I'm going to let n equal 0. And that gives me x equals pi over 4. Then I'm going to let n equal 1. And so I get x equals pi over 4 plus pi, which is 5 pi over 4. And when n is 2, now I have pi over 4 plus 2 pi. And 5 pi over 4. And that's it.